All right, guys. So I'm on page 24 of your packet. So, like I just mentioned a little bit earlier, today we are talking about a new form of quadratics that you haven't necessarily seen before. All right, you may have seen it, you just didn't know what it was called. So, in quadratics, there are three different main forms. So, standard form, which is y equals ax squared plus bx plus c. That's what we've been dealing with exclusively lately. There's factored form, which you guys talked about back in Math 1. That's where you actually factor the quadratic, you're doing big X and all that loveliness. All right? And then there's vertex form. Now, each of these three forms gives you a specific key feature that you can find right off the bat. All right? Standard form, it's typically the y-intercept as well as its direction of opening. Vertex form, what do you think it's going to give you? Kind of in the name. The vertex. All right. So with vertex form, it literally will give you the vertex without you actually having to graph it or find it or anything like that. All right. So that's what we're going to talk about today. We're going to talk about the setup of the vertex form, how to write the equation when you're given the vertex, and how to graph it. All right. So first things first, what we're going to do is we're going to talk about the parent function of a quadratic. Now, does anyone know what a parent function is? Anyone take a guess of what it is? So we mainly use this in function transformations. Think parent-child relationship. So parent functions are your original functions. It's like the default mode of a function. All right. It's basically a function that no transformations have happened to it. We've talked about geometric transformations. Now we're going to look at function transformations. Okay. So it's kind of like its default mode. It's original. Right. That's why it's called a parent function, because if you think of a parent-child relationship, which comes first, the parent or the child? The parent. All right. So the parent function for a quadratic is f of x equals x squared. All right. So let's fill in the x and y values. So I'm going to give you some x values. So -2, -1, 0, 1, and 2. All right. Now, this is a very straightforward plug into the function because all you got to do is just square each number. So what's -2 squared? 4. -1 squared? Nope. 1. 0 squared? 1 squared. 2 squared. 4. Now, we're just going to do a quick graph here. So this is the parent function of a quadratic. So y equals x squared is your most basic form of a quadratic with no transformations. It hasn't shifted, it hasn't stretched, it hasn't reflected, nothing. Now, the pattern for a parabola from the vertex. Okay, what is my vertex? 0, 0 is my vertex. All right. So right here is my vertex. Now, what the pattern is that vertex form is this. F of x is equal to a times x minus h squared plus k. Where the value hk is your vertex. Now, your A value represents the exact same thing as it does in standard form. It typically is your leading coefficient. It is also your way to tell if it's going to reflect over the x-axis or not. So if it's going to open up or down, essentially. All right. Now, if that's our vertex form, let's see if that actually lines up with our parent function. So we said my vertex is the point 0, 0. Now, just for the record, my A value is clearly equal to 1. So if I plugged all of this into my function and simplify it, let's see what we get. So I have f of x is equal to 1 times x minus 0 squared plus 0. So what happens to both zeros? They don't necessarily cancel, we can leave them out essentially because it's nothing. All right, so this will be f of x is equal to 1 times x all squared, which we can just rewrite as f of x is equal to x squared. So even though we put it in vertex form, it will simplify down to its standard form, which is just x squared. Now, we're going to learn how to simplify from vertex form to standard form today, but tomorrow we're not going to talk about going from standard to vertex form until tomorrow because you got to learn a new skill for that. All right? So again, HK, so if you look in place of it, that is where the vertex is. All right, so let's do an example. So first off, before we even do anything graph-wise, what do you think my vertex is? Is it positive 4, negative 5? You sure? Look at my formula again. What's automatically in the formula for my H value? It's negative. So if it turns up positive, what number do you think it is? Negative 4. So guys, this is what you have to be careful with. This minus is part of the formula. All right. The H next to the minus is technically positive. So if it becomes a plus here, this is the exact same thing as x minus negative 4 squared minus 5. So our vertex is actually negative 4, negative 5. So essentially, your x value of your vertex in vertex form, just make sure you flip the sign from point to what goes in the function. Now, if that's our vertex, what's our axis of symmetry? X equals negative 4. So this form also gives us our axis of symmetry right off the bat as well. Because remember, it's just the x value of the vertex. Now, based off of our function, do you think this is going to be a max or a min? Min, how do you know? So in other words, the A value in front of it, or the unspoken A value in front of it, is positive. All right, so it will give you a minimum. So what is the minimum or maximum value? So in other words, what's my minimum value? So we're talking about a minimum value. Remember, the vertex is the minimum. So if we're talking about its minimum value, what part of the point am I talking about?
Y-axis.
Not the y-axis, but the y value. Okay, so what's the y value of the vertex? -5. So remember, this comes from the y value of the vertex. Now, what do you think the y-intercept will be? So what's an easy way I can find it using my function? Plug in what? Not the vertex. The vertex won't give us the y-intercept. Nope. Think about how you write the y-intercept as a point. What value do you always have for x?
0.
0. So what can I do with that? Plug in 0 for x. So the y-intercept, if x is equal to 0, I can plug it in here. So I have 0 plus 4 squared minus 5. So that's 4 squared minus 5. So that's 16 minus 5, which is 11. So my y-intercept is the point 0, 11. So remember, guys, if I ask you to find the y-intercept by hand, you just plug in 0 for x. Especially if it's not already in standard form, because remember, vertex form does not give you the y-intercept off the bat. Only standard form does. Now, let's talk transformations. So before we do anything with transformations, I want to make a quick graph. Okay, so we're going to graph this function off to the side. So I'm going to start by graphing the vertex. So that's at -4, -5. All right. Now my y-intercept is a little too high up, so it's going to be off my graph. So I'm going to just find some quick points that's around my vertex. So I'm going to make a little table. So I'm going to put -4, -5 in the center. All right. Now, let's just do 2 points above -4. So -6, -5, and 2 points bigger than -4. So -3, -2. Now remember, since it's symmetrical, what should be true about these points? So in other words, what x value should have the same values for their y if they're symmetrical? -5, -3, and -6, and -2. All right, they should have the same value. So really only need to find one for one of them. All right, so let's do -3 and -2 because those will give us some positive numbers. All right, so what's -3 plus 4? 1. What's 1 squared? 1. And then what's 1 minus 5? -4. So 5 should also be -4. All right, what's -2 plus 4? -2 plus 4.
2.
2. What's 2 minus 5? -3. All right, so I'm going to take a moment and graph these. Oh, whoopsie. So what's 2 squared? So we did -2 plus 4, which is 2. We forgot to square it. What's 2 squared? 4. What's 4 minus 5? -1. So our graph should look something like this. Now, the last thing it asks us to tell us is transformations. So when we talk transformations, we're talking about going from the parent function to our new function. So whenever you're talking about function transformations, it always starts with your parent. Okay, so if we look at the parent function, which just for reference, I'm just going to redraw right here. So I'm going to redraw my parent function, which is y equals x squared. So this is y equals x squared, which is my parent. Yep. Reynolds, you're needed in the front office. All right. So function transformations are very similar to geometric transformations. So remember when we talked geometric transformations, your very first unit? Remember that? All right. So let's just kind of go through these. So first off, do you think that it reflected any? No. Do you think that it dilated any? So it got bigger or smaller? No. It actually didn't. Now remember, my drawing is not to scale. If we actually looked at it in Desmos, it wouldn't have stretched. Okay. So what does that kind of leave us transformation-wise? Because we know it didn't rotate either. It's the only transformation I did not talk about. A translation. So in other words, it shift. All right. So do me a favor, figure out what my translation is. What's the shift? So I would use the vertex as a point of reference. So go from the parent function vertex to the new vertex. See what you do. Take a minute and try that on your own. So again, you're using your vertices as reference. You're going from your parent vertex to your new vertex. All right, someone raise their hand and tell me what they got as their translation. Amelia. So in other words, what does that mean in layman's terms?
So you went 5 down.
Good. So we go down 1, 2, 3, 4, 5, and then to the left 1, 2, 3, 4. Those are our transformations. So we can write it just like that. So left 4, down 5. Now, if we want to write that like Amelia said in our mapping version, we could say xy transforms into x minus 4 and y minus 5. All right, they're the exact same thing. What do you notice about how we transformed? What's something that's pretty big about how we transformed? Think about the point that we started with versus the point that we ended with. So what point did we start with? What's the point? 0, 0. What point did we end with? -4, -5. What's the connection between that and the transformations we just did? It's the same thing, all right? So if we actually took a minute and plugged in our original starting point, so if I did 0, 0, and I transformed it with 0 minus 4, 0 minus 5, it gives me my vertex. So your vertex form also gives you the function transformations. It tells you how it shifts. All right. So when you graph with vertex form, it's pretty easy to graph if you know its parent form. Now, again, just to restate, this is your vertex form. All right. Now, just to break it down, A is your leading coefficient. Okay, it also tells you the reflection. Okay, so if it's negative, that means it's reflecting over the x-axis or it's opening down. Now, your vertex, you know, comes from HK, but if your HK, so if it's written with a plus H in the formula, what direction do you think you're going to go? So based off of what we did in the last problem, look at the original formula and look at the transformations we got. If I have plus that H value, so like for the last one, it was plus 4. What direction did I go in? Not up. Nope. What do we do 4 up here? So what did we do 4 up here? We went to the left. So if you have a plus H in your function, that means you're going to the left H units. So what do you think minus will be? Right. Now, K. If we have a minus K, so like in our original that we did up top, what direction did we go if we did minus K units or minus 5 units? What do we actually do? We did down. All right. What about plus? What do you think? Up. Now, why am I telling you this? Because this is another strategy that you can use for graphing if you're given vertex form without having to generate a table. Okay? So you could do like make a table with a parent function. So use that original table that we had up top. So with x squared, and then you can do like this right here with the points. All right, because that not only gives you your vertex, but since you also know other points for your parent function, aka right here, and it's really easy to find because you just square that number, you can use that to find other points without actually having to put it into the function. Now again, A still determines the direction of opening as well as its pattern multiplier. All right, so if it's negative, that means we're going to change all of our values to negative. If it's positive, they stay positive. If there's like a 2 or a 3 there, which we'll do in a little bit, you'll kind of see what happens. Axis of symmetry is still x equals h. So whatever the h value is, remember it's negative. In the formula, this negative technically means that this h is positive. So even though it's negative, this h is technically positive currently. Your vertex is still hk. And of course, your y-intercept, you substitute 0 in for x, solve for y. So things we already did. So let's try some more examples. All right. So first off, what is my a value here? -1. All right. And we'll come back to the pattern in just a second. What is my vertex? 1, 3. All right, so we switch the sign here because it's in its natural form. It still has the minus, so that means the 1 has to be positive, and then the 3 just remains whatever sign it is. So what do you think my transformations will be? If I go from the parent function to our new vertex. So not left 1, but right 1. Right 1, up 3. Now, what else do you think is going to happen? There's another transformation. What happens if our a value is negative? It does what? Reflect over what? The x-axis. So it also reflects over the x-axis. Now, before we discuss the y-intercept, let's just take a moment and figure out the pattern that I was talking about. Okay? So first off, let's start with our original parent function. So this is x, and this is x squared. All right, so this is our parent function graph. So I'm going to start with the points that I had up top. So -2, 0, -1, 1, 2. And then 4, 1, 0, 1, 4. So first off, if you're reflecting over the x-axis, who remembers what signs actually change? The y's. Good. So what happens to the y's? They become what? They become negative, or the signs flip. All right. So if I apply a reflection, this is now x, this is now negative x squared. So in other words, we multiply a negative after we take the negative squared. So this is now -2, -4, -1, 1, 0, 0, 1, 1, 2, 4. All right. Now, if I want to find from my parent function, let's say I just want to find what x minus 1 squared plus 3 is. So it has the same vertex as our original function. The only difference is it's not opening down, it's opening up. So what's an easy way I can find it without actually having to plugging in points into the function? So what can I do for my transformations? So remember, if we write in this form, if I'm going right 3, how do I write that in terms of a point? Or right 1, sorry. So guys, like we did up here, how would I write that? My transformations out.
X plus 1,
X plus 1 and
y plus 3.
y plus 3. So we add 1 to our x's in our original, we add 3 to our y's. So for negative 2, 4, what would the new points be? So if I add 1 and negative 2, what is it? Negative 1. If I add 3 to 4, what is it? 7. All right. If I add 1 to negative 1, what is it? Okay. What if I add 3 to 1? 4. 0 plus anything is just 1, 3. All right. What if I add 1 to 1? 2. All right. What if I add 3 to 1? 4. If I add 1 to 2? 3. And then we should still get 7 for our last one. So guys, what I did is I took these numbers and I did plus 1 on this side, plus 3 on this side to all of these. That's how I got there. Now, we can then apply our reflection. So again, we're just reflecting over the x-axis. So what's the only thing that changes? The y values. So if this is x and then our true function, so negative x minus 1 squared plus 3, negative 1, 0, 1, 2, 3. So this is now negative 7, negative 4. This is still 3 because it's the vertex. Okay. So the vertex is the only thing that doesn't change because it's the vertex. All right. Negative 4, negative 7. Now, the reason it doesn't change is that if we also went from this one to this one using just our plus 1 plus 3, okay, negative 4, negative 2 plus 1 is still negative 1, negative 4 plus 3. What am I doing? Ugh, Lord help me. So, okay, this is kind of an example of what not to do. So in other words, you would have to go from here first and then go to here second, applying the transformation. Okay, so in other words, you do reflection first, then the translation. So this would actually be, if I add 3 to all of these numbers here, this would be -1. This would be +2. So this would be +2, -1. All right, sorry guys. So if I graph this, I have my vertex 1, 3. I have the -1, -1, and the 3, -1. Then I have the 2, 2, and the 0, 2. So my graph looks something like this. So the pattern is that our x squared values become -x squared. So our y-intercept we already found, which is what? So without having to plug it in. 0, 2.
Can you do all that just to find the y-intercept?
No. You can just plug in 0 for the y-intercept. Okay. So let's do example 3 together because I pulled a stupid apparently. All right. So a value is what? -1/2. So in other words, if we started with our parent function x squared, what happens to those x values? Or what technically will happen to it? It'll be multiplied by what? Right. So in other words, our original y's will become these. All right, so just for reference, and you guys don't necessarily have to write this down, but still using my same table. If I multiply them by -1/2, okay, what's 4 times -1/2? So 4 times a half is what? 2 times a negative? -2. Well, I'm just taking these values and then applying that. Because the x values are going to be the same. Because if I plug in -2 to x, -2x squared is 4. 4 times -1/2 is -2. All right, so 1 times -1/2 is -1/2. 0 is still 0. So this will be -1/2 and -2. So our transformations are what? So what's my shift? So am I going up, down, left, right? What am I doing? So we're going right 2. And then what? Not down 1, but so just from this function, guys. Up 5. So right 2, up 5. What else am I doing? Right, so we're going to do a dilation because our values technically got smaller. All right. So we'll talk about this in a second, but this is called a vertical compression by 1/2. And what's the last thing I'm doing? A reflection over what? X-axis. So what's my vertex? So 2 and what? 5. What's my axis of symmetry? Good. Now we're going to graph at least 5 points. So we're going to use this table, this is why we created it, to help us make our other transformations. So all we got to do now is just add the 2 and add the 5 to each of those points. Okay? So we're going to do xy, and we're going to transform it to be x plus 2 because we're going right 2, and y plus 5 because we're going up 5. So if I make this table, okay, what's negative 2 plus 2? 0. What's negative 2 plus 5? 7. Up. Positive 3. What's negative 1 plus 2? 1. Think about this carefully. What's negative 1/2 plus 5? So 4.5 or 4.5. You can also say it is 9/2. So 9/2, or you can say it's 4.5. So we know that 0, 0 will give us our vertex. Now, we know our y's, we'll just repeat. So we can rewrite those. We just need to find our x's. So what's 1 plus 2? 2 plus 2? 4. So if I graph this, I have 0, 3, 1, and then 4.5, so about right here. 2, 5, 3, 4.5, and then 4. Wait. Yeah, I flipped these. This should be 4.5. This should be 3. So if I graph this, it'll look something like this. Now, what do you notice about this graph compared to our parent function? So our parent function's up here. So we know it's flipped over and we know it's shifted, but think about the dilation itself. I called it a vertical compression. Did my graph get wider or did it get thinner? It got what? It technically got wider. Okay? So there are 2 types of vertical compressions and stretches. Okay? I like to think about it like a rubber band. So if it stretches, you're actually getting thinner. If it compresses, you're getting wider. So, you have a rubber band. This is your parent function. If I stretch it, what's actually happening? It's getting thinner. If I compress it, it's getting what? Wider. So the rule is that if it's a fraction as your value that you're multiplying by, your graph will get wider or it's going to compress. If it's a whole number, so like anything greater than 1, it'll stretch. So guys, to be perfectly honest, I'm kind of going the around your butt to get to your elbow type way. You do not need to do all this if I asked you to graph this, okay? I just need you to, at the very least, recognize the transformations. Now, if we wanted to, we could just find the vertex and then just plug points around it into our function. Okay, that's totally fine as well. But if you wanted to use your transformation so you didn't have to plug and chug so many times, you could do it this way. All right. So let's just do one more example and then we're done. So here's my function. What do you guys think? Is it going to open up or down? Up. Why? My A value is positive. Now we're going to come back to transformations in a second. What's my vertex? -1, -10. So since this is positive, that means we have minus -1. And then this one is just stays as is. So my axis of symmetry is where? X equals -1. All right. What's my transformations? Dilation by a factor of 3. So since it's a number bigger than 1, we're going to call this a vertical stretch by 3. So again, just to make a note, vertical stretch, your A value is greater than 1. Vertical compression, your A value is between 0 and 1. So in other words, it's just a fraction. Now, and that's not including the negative. Okay, so if the negative's there, remember that dictates the reflection side of it. You ignore the negative whenever you're trying to determine the dilation. Okay? What's the other transformations that we got? So we don't have a reflection because there's no negative on the A value. But what about translations? We go left, what? 1, and then what? Down 10. All right. So what would my y-intercept be if I plug in for 0? So guys, if you're going to do that, I got to take a call. All right, so what do you guys get for the y-intercept? Focus.
I got -10.
All right, so plug in 0 for x. So what's 0 plus 1? 1. What's 1 squared? 1. What's 1 times 3? 3 minus 10. Negative 7. All right, so now we can do some graphing. All right, so I got my vertex first, so that's -1, -10. Now my y-intercept is at 0, -7. So symmetry-wise, if I have one point at 0, -7, where do you think the other point with a y value -7 is going to be? What x value? -2. All right, and let's find one more point. So let's plug in 1 in for x. So what's 1 plus 1? 2. What's 2 squared? Times 3? 12. What's 12 minus 2? 12 minus 10. 2. So we would also have a point at 1, 2. So symmetry-wise, where would the other point be? -3, 2. So guys, we're using our axis of symmetry, which is right here. It's the same distance on each side of the axis of symmetry. So this would be like this. And again, as we can see, it did in fact get thinner. All right, so domain and range. So yeah, it's always all real numbers for the domain. What's my range? So what's my lowest y value? -10 to infinity. We know infinity has a parenthesis. What goes with a -10? Bracket. All right, any questions on this? All right. Okay, so we're going to stop here for today and come back to these last 3 examples tomorrow. So your homework for tonight, I just want you to do, let's say 5 through 12. And 16 and 17. So I want you to do number 5 through 12 and 16 and 17. So homework is numbers 5 through 12 and then numbers 16 through 17. This is page 27 and 28. So it's between page 27 and 28. Yeah. So you guys got some time before class ends, so you can go ahead and get started on this. Sorry that my lesson was kind of wonky today. I'm clearly not feeling it today.